Listo, pues muchas gracias a todos por estar aquí. Gracias por salirse del Gather Town y venirse para acá a la presentación de Safia Kedad-Sidhoum. Voy a leer la presentación de Safia, una biografía. Safia Kedad-Sidhoum es profesora de investigación operativa, de investigación de operaciones del Conservatoire National des Arts et Métiers, CNAM, en París, Francia. Dirige el equipo de optimización combinatoria del laboratorio CEDRI, que es muy fuerte en el área de optimización. Ella recibió su doctorado en Ciencias de la Computación en el 1997 por l'École Centrale de París, una escuela también muy reconocida en Francia, y su título para dirigir investigación de la Universidad Sorbona, Sorbona, de Francia, en el 2010. Ella, además de ser muy buena investigadora, trabajó en una empresa que se llama Dynasys como gerente de proyectos en planificación de la cadena de suministro. Y ha sido profesora asociada desde el 99 hasta el 2017 en la Universidad Sorbona en Francia y luego se integró a la Universidad CNAM. Ella ha participado mucho en la Asociación de Investigación de Operaciones de Francia junto con la Asociación de Investigación de Operaciones de Europa. Ella es parte del comité organizador del Challenge ROADEF desde el 2012 y es parte de las organizadoras del Working Group in Lot Sizing. Ha recibido numerosos premios. Uno muy importante es un premio de Google en el 2011. Y además de la planificación de la cadena de suministros, es lo que nos va a hablar hoy, su interés de investigación es la optimización combinatoria, la programación matemática, la planificación y el dimensionamiento de lotes. Safia es autora de más de 30 artículos en revistas internacionales. Y ahorita voy a cambiar en inglés para que me escuche ella. She's a great researcher, of course, but also she's a great friend of mine. I have worked with her, and it's really a pleasure to be with her. And so I'm very happy that she accepted today to be with us. So Safia, please, you can start your presentation. Thank you.
Okay. Thank you, Yasmin, for the introduction. I will share my screen. Okay. Okay, could you see my screen?
Yes, we can see it. Perfect. Yes.
Okay, great. Thank you, Yasmin. Thank you. I'm very happy to be with you today, even if it's not on site, but I am very happy to talk about this topic about sustainable lot sizing. I have worked some years around lot sizing, and I will focus today on some presentation around what is called sustainable lot sizing. Before starting, I will recall some basics in lot sizing field. I don't know if you are you know this domain of operational research, which is related also to production planning. But I will start by giving some basic results in this field. I hope that it will not be redundant regarding your background.
No, it's going to be perfect. So.
Okay, thank you. And then I will focus on these emergent applications in research, but also in industry. There are many new problems arising around sustainability. And I will talk about three of them. So green lot sizing, energy management, and lot sizing and remanufacturing. I will perhaps present you the backgrounds and then start with the first application, and then perhaps we can just exchange about your questions or remarks about this application before going to the next one, and so on. Okay. So lot sizing is a domain related to operation research, and it's a domain that is related to the planning decision in tactical, for tactical decision. There are some strategical decision, tactical decision, and operations one. The planning production decision related to lot sizing are concerns planning horizon around months or weeks, but not really days or hours. So what is the core problem dedicated to this field? The core problem, a very basic problem, is a single item problem where we have one product, and this product we have some demand to satisfy. So here we have demand 1, 2, 3, and 4 related to 4 time slots, which constitutes what we call a planning horizon. So we have this demand, and we need to satisfy the demand who comes from, for instance, customers. And to do that, we have to define which quantities are going to be produced over this horizon. So for instance, we can order a quantity which is related to the 2 first demands, D1 plus D2, in the first period of the horizon, and then D3 and D4 on the third period of the horizon. So how can we decide? There are other possibilities. This is just one of them. And how we will decide which is the best to meet this discrete demand is it will be done regarding the inventory induced by satisfying this demand, so by the productions. In other terms, if we look at this production, we see that we will produce the demand D2 one period in advance, so that this demand will have to be put in inventory for one period. So the profile of the inventory here is D1 in the first period to meet this demand, and D4 in the third period to meet this demand. So we will have some inventory holding cost that will be taken into account to describe this solution. So what we have to do is to find the best compromise between the total production cost, which is constituted by unitary production cost, and what we call a setup production cost, and also the inventory total cost. Here, I have one order in the first period. So the setup is, we have a fixed cost in the first period, a fixed cost in the third period, and variable cost related to the total quantity D1 plus D2 in the first period, a variable cost related to the quantity D3 plus D4 in the third period, and then we have to hold in inventory D2 for one period and D4 for one period. So how we can characterize the best solution to meet this demand is we aims at finding the best balance between production total cost and inventory cost. So this very basic problem, this core problem, is what we called the uncapacitated lot sizing problem that will be denoted ULS in the following. And it has been first introduced by Magna and Within in 1958, so quite a long time ago. And this problem was selected as one of the 10 most influential publications in the first half century in the journal Management Science in 2004. So many research around many variants of this problem, many solution approaches, and I can say that this problem is really the one that you have to know if you try to keep or catch something around lot sizing field. So starting from this seminal work of Wagner and within, we have a huge amount of books, articles, and research in this field. I mentioned here 4 books, which are quite recent, but there are many others and many surveys in this field. So you can find many material if you want to learn more about lot sizing field. And I have to say also that in industry, in industrial application, there are many advanced planning and scheduling tools, what we call the APS tool here. And practitioners are using these tools, and they embed, most of them, some basic algorithms around production planning and lot sizing field. So this is now mandatory to have in each APS tool a production planning core algorithm to derive the production plans. So it is widely known in academic field, but also for practitioners. So what we can say about this problem, and we start by the basic formulation. One of the most well-known formulation is the following. So we have 4 parameters to describe the ULS problem. The first one is the demand. So I recall that we are just looking at the single item variant of these problems. So we have one product. The demand is a discrete one over a planning horizon, dt. We have a production cost, which is unitary production cost, the setup, which is the fixed setup production cost, and a unitary inventory cost, which is defined each time we have to store 1 unit of product in inventory at period T. So the objective is to compute a production plan over this discrete planning horizon, and we want to minimize the total cost, as I said previously. What are the decision variables of what we call the natural formulation of this problem? We have 3 variables. The quantity produced at each period, which has been defined previously in the illustrative example by the colored rectangles, and the derived inventory that is induced by these produced quantities, and also a setup variable, which is a binary variable. So the first 2 ones are continuous, but the third one is an integer variable, which is equals to 1, which is equal to 1 if we produce a strictly positive quantity, or 0 otherwise. So those are the variables that we have to that we need to formulate this problem. This formulation is also well known as the aggregate formulation in lot sizing field. And the model is the following. We have to minimize the total production cost, which is constituted by the variable cost and the setup, and also the inventory cost. What are the constraints? We have flow conservation constraints, which says that if we have 2 periods, let us say T-1 and T, the entering stock, which is ST-1, plus the production at this period must be equal to the demand that will be consumed at this period, plus what will be left in stock at the end of this period, which is T. So this is a very classical flow conservation constraints, which is the core constraints of this model. Then we have a coupling constraint, which relates the production with the setups. The domain variables of the domain variables, which are given here by continuous variables and binary constraints, we can set the bounding for the production as at each period of time. If we are in period T, for instance, here we can say that what will be an upper bound, a good upper bound for the production is the cumulative demand until the end of the horizon. So the total quantity that you need to produce if no production occur after T, so you have to produce the total demand until the end of the horizon. So this is the aggregated formulation, the natural formulation for this problem. And as I showed you before, one other representation of this problem is the fixed charge network flow model, which derives from graph theory. So we have here these arcs are the production arcs, and then the horizontal ones are the inventory arcs, and the demand is represented here. Okay, and what we have to deal with is only the setup costs each time we have a strictly positive value on the arcs, production arcs. We have to compute these setup costs, so F1 for the first period, F2, etc. for the other periods. Okay, so this is why we call this model fixed charge network, because we have to deal with setup costs. So what is important here, if you look at a solution that comes from my first example, the illustrative example, you see that the shape of the solution is specific. So you see that here we produce at the first period to meet the demand of the two first periods of the horizon, and then we store a quantity for meeting the demand D2, and it's exactly the same for the third period, and we store here the demand for period 4. So the shape of the solution regarding the graph aspect is very specific, and we will see that we have a very important dominance property of these solutions, which leads to solve the problem very efficiently. So the structural property is related to the minimization of a concave function of the flows on the network, since we have these setups cost to consider. An extreme point optimal solution will exist, and we can prove that these extreme points on the sets defined by the network flow constraints are spanning trees. That means that they are connected subgraph containing no cycles. So what is the insight behind this property? The insight is that if, I will try to show you directly here, if it is interesting in terms of the induced cost to produce in period 3, for instance, so there is no motivation to have produced some quantities before. It's better to produce all this quantity which was in stock at period 3. If it is better to produce it before period 3, then we delete this arc and all the quantity will be stored previously to meet the demand of period 3. So here we can see that having both the arcs in red here in the graph is not a dominant solution, since we can balance the flow either in arc from 0 to 3 or from 2 to 3 regarding to the cost. So we have a dominance property, and all the solutions that we have to check are the solutions that are spanning trees, that have this shape in the network flow model. Okay, so this property is very well known, and it is called the zero inventory ordering dominance property, meaning that we produce if there is nothing left in stock at the previous demand. Okay, so why this property is really important? So this is the property that Magna and Within found so in their seminal work, and this property shows that if we have an order, this that means that we have a production. This order will cover an integer number of periods of demand. Okay, this is really important. Okay, so if we produce, we will cover the demand for an integer number of periods, consecutive periods. And then we will have just to check when computing an optimal solution, where we will decide to produce. So these production points, or these ordering points, where there is no inventory at the beginning of the period, are called the regeneration points. And we only have to find where to put these regeneration points in the solution. So if we go a step further, we can just set up a dynamic programming algorithm that is really a basic algorithm using the Bellman principle. And how we can do that? We will put Ti and Ti plus 1, 2 consecutive regeneration points. And we will compute the total cost related to this interval, which will be given by the setup cost in period Ti plus the total production cost related to the quantity that will be covered by the interval Ti plus 1, and then the inventory holding cost that is derived from these quantities that have to be stored until period Ti plus 1, minus 1. So this computation leads to a recursion formula, which will be the basis of the dynamic programming algorithm. So if we denote by GT the minimum cost of production plan from period T to the end of the horizon, then we will have a recursion, which is this one. And this recursion will just have to check where we have to put these regeneration points from T plus 1 to the end of the horizon. So this is a dummy period, which represents the end of the horizon. Okay, so the optimal value will be given by T is equal to 1, the value G1, okay, G of 1. And computing this formula is can be done in T squared, in O of T squared. So the complexity is really interesting, since T represents the number of periods, and this number of periods usually are not very, very high when dealing with real applications. So this is the seminal work of Magna and Within, and this is the core results in lot sizing field. So two things: the dynamic programming of Magna within, with a very good complexity, and this ZEO property, which is really useful to analyze lot sizing problems in general. So another intuition behind this is the model of another model is using shortest path models. So if we come back to our illustrative model here with this period, this is a dummy period just representing the end of the horizon. We can just say that an arc between two nodes exists if a production is set up at the origin of the arcs to cover the interval ej-1 for the arc ij. And then what we have to compute is the related cost, so the setup at this period, plus the production cost for covering the interval, plus the induced holding cost. So we can just derive a shortest path model with these cost computation. And if you need to have the best solution, you have just to compute a shortest path in this graph. And this shortest path can be computed using Bellman algorithms. And so you derive the same complexity as the one proposed by Wagner and Within for their dynamic programming algorithm. So it's just another representation of the solving method. Okay, so what we have to recall also is that this O of T squared algorithm, which is the seminal one, have been improved by many authors. I just mentioned here Wagelmans et al. And Agarwal and Park. So there are many different approaches. One of them is based on some geometric arguments. I will not develop this here. It's the one proposed by Wagelmans. And he proposes to reformulate the problem by removing the inventory variables. We can do that because we have an equality for the flow conservation constraints. So we can remove one variable, either production or inventory variables, to derive the other one. And what he did, he just compute the minimum of the lower convex envelope of the points related to periods and related costs. And this is a very nice paper, and we can just have T iteration and in O of log T, because this logarithm comes from a binary search proposed by the authors. So we can improve the complexity, and now we know that ULS can be solved in O of T log T. So we can use the dynamic program of Wagner and Within, since the complexity is reasonable, but the best one is this one, which has been proposed in the early 90s. Okay, so before going through the application, I don't know if you have some questions about these basic results. Otherwise, I'll continue.
Yes, continue, Safia, because there are no questions in the chat. Okay, great. So what I wanted to show you in this talk is some new application in lot sizing. So on what kind of problems we are working in research, and also what are the practitioners and the industries are looking for around this production planning field. And I will mention 3 applications. So these applications have the opportunity of working exactly in these domains. So I will give you some, it's not exhaustive, but I will give you some results around these applications. So feel free to ask me if you need more
more details, but there are some papers around the results, and I can send you the paper if if you are interested in this application. So I will start with green lot sizing. So what I mean by green lot sizing is solving lot sizing problems, real lot sizing problems, by looking at some environmental aspects. And for the first application, I will take into account carbon emission constraints. So I have been working in this field with some other colleagues, so Nabil Apsi, Stéphane Dozer-Pérez, Bernard Pence, and Christophe Rapin, who are French researchers here. And we wanted to revisit lot sizing classical problems in the lens of green aspects and carbon emission constraints. So how the classical problems behaves if we try to put some green aspects in the constraints or in the objectives. And why we do that? It is because there are many motivations to work on this field, because the legislations are evolving and are enforcing people, industries, to control their carbon emissions. And the aim is to propose some models that are able to improve the computation of the carbon footprint of the product. So how we can say that this product has exactly this level of footprints or not. So we need to have some models to deal with that. And so the companies are facing also some new constraints that will force them to reduce their emissions and still minimize the production and the transportation costs. So those are two contradictory objectives, since if we want to minimize the costs, we can have a very bad carbon footprint. And if we want to be very virtuous in terms of environmental aspects, we will have a very high cost induced by the solution. So we have to find a good trade-off, or at least to provide some new models that tries to give some answers in this context. So what we did, we tried to work on lot sizing with carbon emissions. So there are many works dealing with carbon emissions that are modeled in the objective function, but the results show, and the experimental analysis shows, that the behavior of this model are closely related to minimizing transportation and production costs. So there is nothing new that what we know regarding the classical model. So what we tried to do is to introduce some constraints, to embed something which is really which will change the shape of the optimal solution regarding to these green lot sizing aspects. So our models provide something new regarding to the literature. Is that we have to deal with what we call a variable carbon emission constraints, meaning that we will take into account the quantities that are supplied over the planning horizon, which was not done before before our work. So I have to mention that these these results, have been published in 2 articles, one in EJOR, European Journal of Operational Research, in 2013 and 2016. And so I can send you the papers if you need more details on the results. So I will just provide part of the results. So our focus when we started working on this problem was to analyze the complexity of the problem. So what will change in terms of complexity analysis? Do we have some structural property still valid or not? Do we lose the polynomial cases when adding this constraint, etc.? So I will talk a little bit on that and provide perhaps some insights for one case, the polynomial case. And in the second part, I will just mention what we have done regarding to the fixed carbon emission in the one specific case. So we will a little bit change the definition of the problem here, but you will see that the modeling of the problem is almost almost the same as the one that I have previously presented. So we will consider a multi-sourcing uncapacitated single item lot sizing problem with carbon emission. So what is multi-sourcing here? Multi-sourcing means that we will combine a production plus a transportation, okay? So we will consider that we have M means of production and transportation modes. So we can consider that we have a combination of a production location and a transportation mode. We still have a horizon of T periods, and we propose to model 4 different ways of taking into account carbon emission constraints. The first one is to limit at each time period of the horizon the carbon emission. These models are called the carbon cap models. So we have just to put an upper bound on what we can use in terms of carbon emission for supplying this single item product. Then we have another setting, which is the cumulative one. So that means that the amount of unused carbon emission of a given period can be reused at the following period. Another model, which has been, we analyzed this model, but it was previously proposed in the literature, is to consider that we have an amount of carbon emission that we can use over the whole horizon. This extends the cumulative one. So what are the inconvenience of this kind of modeling is that if you consider the whole horizon, then for the first periods, you can use a lot amount of carbon emission and then try to equilibrate things at the end of the horizon, which is not good in terms of practical setting, because usually the first periods are the ones that will be really used in terms of real solutions. So having something which is really bad at the beginning of the horizon is not useful for practitioners. And the last model that we try to analyze is the rolling horizon model, which consider that we can do some compensations in terms of carbon emissions, but over a fixed number of periods, okay? So we can notice that this rolling carbon emission includes the periodic case, if we say that the compensation are restricted to one period, or the global carbon emission case, if we extend the compensation over the whole horizon. So this covers the rolling here case, cover this one and the periodic one. Okay. So in terms of mathematical programming models, so we come back to our parameters definition. We have the demand for the single item. We have a holding cost, which is the same, which depends on the quantity stored in inventory. And here, rather than having the production cost and the fixed cost, we have just changed a little bit the setting and says that it is the unitary supplying cost and the fixed supplying cost. Okay, so PT and FT are exactly the same as the ones considered for ULS, but here we have just one costs related to each mode for the unitary cost and the setup cost, fixed setup cost. And what is new here in terms of parameter settings is that we have parameters that measures the environmental impact of supplying 1 unit for mode M at period T, okay? And we have a threshold on the limit that is allowed for this period, which is defined by capital E here in the model. So we will say that a mode is ecological if the impact is below the threshold, okay? Okay, so let us see now what are the decision variables. So we have the quantity supplied at each period, which will be defined here by the X variable, the Y variable for the setups, and the inventory carried from one period T to period T plus 1. So those variables are exactly similar, are similar to the ones of ULS, so I will not develop more than that. The only thing that changes is the indice related to the mode, because we consider that we have big capital M modes to supply the demand. So here is the mathematical model. So this problem is an uncapacitated single item lot sizing with this slight modification, which is multi-sourcing, since we have these modes. And this core model, the first model, is without carbon emission constraints. Okay, so we come back to the total cost. So supplied, variable supply cost, fixed supply cost, inventory cost. Here we have the flow conservation constraints. Okay, so the total quantity supplied at period T minus what we have, what we have in inventory is equal to the demand plus what will be left in inventory at the end of the period. So this is the linking constraints, and those constraints are the domain variable constraints. Okay, so this is almost the same as what we get in the ULS model mathematical formulation. So now let us see what will change, what we have to add in this model to take into account the carbon emission constraints. So for the first case, which is the periodic one, what we have to do is to compute the amount at each period of supplied quantity, which is weighted by the environmental impact. This is the total quantity that is supplied at period T, and the relative value has to be lower than this threshold. Okay, so in other words, we can just reformulate this expression, and we get this formula, which is model the periodic carbon emission constraint. So here at the first, so if you look at these constraints, it seems that this constraints is related to a capacity constraints, but here it's completely different because we don't have to respect a threshold, but we have to compensate between multiple modes to meet the demand. Okay, so there is this notion of compensation, which is not embedded in the classical capacity constraints. So this is completely changes the analysis of the model, since it does not behave like a capacity constraint. So this is the first constraints. Then we have the cumulative one, which is almost the same, but we have to reconsider what is not consumed at the previous demand. The global constraint is the same as the cumulative one, but we have to do the summation over the whole horizon. And the rolling one has to take into account this value big R, which is the length of the interval where the compensations in terms of carbon emission can be done, can hold. Okay, so I will not go through the details. I think you can just follow the talk without having all these details in mind. But if you have some questions, I can answer after the presentation. So what? So the first thing that we have, when you analyze a lot sizing problem, the first thing that you try to do is to see if this ZEO policy that I mentioned earlier for the ULS still holds. Why? Because if you have this policy, you can try to find a polynomial algorithm for the problem, because the structure is really nice, and then you can decompose the problem and try to solve it efficiently. So this is really the first thing that you have to do. And we did it. We tried to see that over the different variants of these problems. And we start with the periodic carbon emission constraint. So this problem, so we were interested in this constraint in addition to the other constraints of the basic model. And so few observations. The first one is that we have some dominances between modes. So if you have two modes, one which is with a cost lower than the other and also an impact lower than the other, so you can just remove this mode M2 and just keep M1 since it dominates the other one. And also what is really interesting is to see that in any solution of the problem, you have to use at least one ecological mode, so the one where this value is lower than this value, because otherwise you will not you will not be able to be to have a summation which is lower than 0. Okay, so at least one ecological mode at each period. So what we found in terms of structural properties, what we derived, we have shown, based on a very classical Bender's decomposition approach, that there is a dominant property, a dominance property, and this dominance property says that there is at most two modes in each period that can be used in an optimal, so there exists some optimal solutions, where at most two modes in each period will be used, one ecological mode and possibly one non-ecological mode. So if you can use only the ecological one, because the cost leads to that, so it's okay. Otherwise, you have to compensate the non-ecological one, which is usually less costly than the other one, with one ecological mode. Okay. So this is interesting. Then, thanks to this property, we show that the periodic problem can be reformulated as an incapacitated multi-sourcing lot sizing problem, a classical problem, but with m squared modes using O of m squared t operation. So I will not go through the details for that, but why I wanted to show you these results, because the corollary of these results is that if your lot sizing problem is easy, adding the periodic carbon emission constraints will not derive to a difficult problem. The whole algorithmic complexity will only be increased by a factor of m squared. So this is the meaning of these results. is that if you know that your basic multi-sourcing problem is easy, then you can have an efficient algorithm to solve this problem, okay? There is a small restriction in these results, is that we are dealing only with linear supplying costs. Okay, and then I will go a little bit faster, sorry. What we have also shown is that our famous ZEO policy still holds for the periodic case. Okay, so this is a nice results, because we have been able to derive a polynomial algorithm thanks to this property and the previous one. And the results, so I will not go through the details, but we derive an algorithm which is based on dynamic programming, and which is, you see, it's not exactly the same complexity as the one for ULS, but we add here a factor of m squared log m, which is related to the management of these periodic constraints. Okay. So what we can say about cumulative carbon emission, we can say here that the first property, which is at most 2 modes in each period, still holds. This dominance property still holds, but unfortunately, we lose the ZEO property in this case. Okay, and we tried to find a polynomial algorithm by other ways of decomposition, but it appears that the problem is NP-hard, even on stationary instances, so instances that are not related to time dependency with unit demands. So the proof was based on subset sum problem. So the polynomial cases, we have only the periodic one, and the cumulative one is not easy so far. What we know about the global and rolling carbon emission constraints. So the global case is NP-hard. It uses the same reduction as the cumulative one. And there are some open questions regarding the complexity for the rolling case, because if you see, when we limit the interval length R to 1 period, then we have the periodic case, which is polynomial, but when we set up this case to T, we know that it is NP-hard. So there are perhaps some cases that are polynomial, but others that are NP-hard. So there is some question arising in this case. Okay, so I don't know if you have some questions about this case. I'm sorry, because, okay. So I don't know.
¿O le dejamos que siga?
Because I will change to another problem, so I can keep all the questions at the end, if you prefer.
Yes, I think we keep the questions at the end, Safia. Okay, so continue, please.
Okay, thank you. So another application, which is really interesting and really emerging and challenging today, is all what we can do around energy management. So I will show you two things. So two different works. First one related to energy management for production, which is a joint work with Nabil Absi, Christian Artigue, Sandra Ngeveux, and Omar Sadi. We presented this work in our international workshop on lot sizing in 2017. And also one application around the incentives of energy markets, which is a more recent works with other colleagues. So to just try to show, to deal with the opportunities offered by these energy markets. So the first application concerns data centers and smart building. And this application, our starting point for this study was energy optimized building in Laboratoire LAS in Toulouse. So they have a very nice laboratory, and they were interested in trying to find some new models to for the management of the battery that is related to this microgrid. And they have a battery that was possibly able to store energy coming from renewable energy. So I will just explain the basic assumptions around this application. So we have a set of jobs in this laboratory. We have some computers, some machines here, and some jobs that have to be scheduled in these machines. These jobs consume some energy, and this energy, part of this energy depends on whether the machine is switched on or off, and a variable part depending on the tasks that are currently in process. Okay, so to sum up, you have just to remember that the machines are energy consuming, and each task will require an amount of energy at each period of time. And the goal is to optimize the total energy cost induced by executing these tasks on the machines over a fixed discrete horizon. In this chain, in this microgrid, there were two, to simplify, I will present just a very simple setting. We have two sources of energy, one which is called non-reversible source. That means that we can have photovoltaic panels or energy coming from renewable energy sources that are only able to provide energy, okay? And what we call reversible sources, which are the batteries that are able not only to produce energy, to supply energy, but also to retrieve, assuming a limited capacity. Okay, so non-reversible can be, I think I said something wrong before, but non-reversible source is the production source, electricity, and reversible source is the one where you can put an amount of energy and retrieve an amount of energy. These sources are characterized by some efficiency functions. Okay, so you have you can relate the amount of usable energy regarding to the cost, and those efficiency sources are related to the nature of the sources. So different kind of batteries, for instance, or production sources. And how we can get the cost related to an energy demand, we just have to use the inverse of the efficiency function in this case, and then we can have the cost related to what we'll collect in terms of energy amount. So those are the characteristics of the energy sources. So what was the general framework in our work? We have two phases to tackle the problem. A first phase, which was the scheduling phase. So this phase is related to find a good schedule that minimizes the production cost. Here, we only look at the non-reversible source, so the production cost, the production source, sorry. And the output is an energy demands over the planning horizon. And in a second phase, we will try to see how we can meet these demands using the batteries, okay? So I will call non-reversible source by production source, and the other one by batteries. So the lot sizing phase here appears when dealing with the batteries and the production source. And the goal was to try to see how we can use what is the best way to use this battery to lower the cost of the energy demand derived in the scheduling phase. Okay, so the output of this phase will be a production plan, but which is not a classical, a standard production plan regarding items or physical products, but a production plan regarding to energy amounts, which is a little bit different than the classical framework. So our work focuses in this phase, and I will show you in terms of lot sizing models, what are the novelties when dealing with these energy demands. So I'll come back to the classical model again. We compute a production plan. We want to satisfy a demand, which is related to the energy demand. And we have some limitation because we use batteries, and the batteries have some limited capacity. So what are the parameters? We have the demand here. What is new here is the capacity of the battery. The efficiency function that we will use to compute the cost and to compute the amount that we can get from the battery. So one efficiency function will be related to the production source here, and two efficiency function will be related to the batteries. One to represent what we can get from the battery, so the production, and the other one what we can retrieve, what we can produce and what we can retrieve from the battery. And another new parameter is related to the losses that will be observed, because here when dealing with energy on batteries, you have to take into account that from a period to another one, you will lose a specific amount stored in this battery. So the model is quite different. And here we have to add, we have this classical production variable, this classical inventory variable, but here we have two other variables, one related to the energy collected by the battery, and the other one, the energy produced by the battery. So perhaps the best thing is to show you an illustration here before going through the model. So how we extend the network flow representation in this case, we extend it by doing that. We have, so the classical model is this one. So we have, so you remember, we have a demand, we produce and we store, okay? Here, we have to separate the storage phase from the production phase, because what will occur between production and the batteries have to be modeled in a finer way. So we have here the storage arcs are here, okay? Here are the production arcs, and then you can put an amount produced in the battery, and you can retrieve an amount from the battery to meet the demand which is here, okay? So we have to modify a little bit the network flow model, because we have to work with these two values which we have to define. So if we produce, do we have to put in the batteries, or to use complete all the production to meet the demand, or we will not produce, but we will retrieve from the battery a quantity that will be used to cover the demand. So you see, this is a slight modification, but it has a big importance in what follows. So here is the model. So you see it's classical here. This is a conservation flow model, but here we work with these both variables, those two. Here are the costs related to the production source. Here are the amount available regarding to the efficiency of the battery. And here is the function related to the losses. So if you lose something because of the length of the horizon, okay? So what we try to do, it's almost the same as the previous application. We try to see what are the structural properties, what are the dominance properties, so we can solve the problem efficiently or not. And we have something which looks like the ZIO property policy. Here we have a dominance property which says, so it's really intuitive. This is not it's very easy to guess, is that there is a dominance between what we will retrieve and produce in the battery. Why? Because we can easily see that either we use this arc, so we put an amount of energy in the battery, or we retrieve an amount from the battery. We will not activate both arcs in the solution, because if it is more interesting in terms of costs to put in the battery at this period, there is no motivation to use what was inside the battery at this period of time. Okay, so it's exactly the same analysis as the ZIO analysis. So we have this property, and just to show you the different model that we looked at. So they are all summarized in this table. So perhaps just a few elements around that. So we have to deal with different assumptions regarding to the storage efficiency functions. So we consider different settings. The function is proportional, affine, concave, convex, or piecewise linear. And this case in practical setting is very interesting. Why? Because if you have a nonlinear efficiency function, you can usually use approximation with piecewise linear functions to represent this nonlinear function. So you can see that this case could generalize many interesting and basic cases in practical settings. Okay, so so for the storage efficiency, we have also considered different cases. Here, the identity function, the proportional function, the proportional losses. If you have a loss which is proportional to the amount of quantity stored in the battery. And just, I will not go through all the details, but there are some very easy cases. So the first line represents some easy cases because it is more or less related to the just-in-time production. And if we introduce some affine functions, the complexity is greater, the bound, the worst case bound is greater, but still polynomial. And the concave case becomes NP-hard when the efficiency of the battery is proportional. So we have no fixed part here, but it's still NP-hard. And we show that in this case, so for the piecewise linear case, we have a weak NP-hard case, and we derive a pseudo-polynomial dynamic programming for this case. So I do not have all the numerical experiments, but our colleagues in the LAS in Toulouse use these pseudo-polynomial dynamic programming algorithms to solve the whole problem, and they are using it now in their decomposition approach with scheduling phase and lot sizing phase. So it was really nice to see that we provide something which was useful for the practitioners there in Toulouse. Okay, so the other points related to this energy management aspects is related to market incentives. So this is a recent work with Orange, which is the French company of telecommunication in France. And what was the motivation? Their first motivation is to try to use the batteries that were primarily installed as backup in case of power outages to store some energy when the production prices are low, and then to use this amount of energy when buying some energy is very high. So they try to use these batteries because these batteries are not are there for backup. So part of the capacity can be used just to play with these energy prices over a planning horizon. And what we did is we try to look at different contexts. So the first one, when the energy prices varies, we try to use the battery when the prices are high. This setting is related to what we call the retail market in energy markets. And another possibility is when the energy demand is very high, what we can do to stabilize the grid. We have two alternatives. Either we produce more energy to satisfy the demand, or, and this was really nice because it was quite new in the literature, is to ask some consumers, so energy intensive consumers, for instance, the consumers of Orange, to reduce their consumption. And we call that performing a curtailment, but this is done by offering them a reward. And this is what we call the curtailment market. So Orange wanted to see if we can play with both markets when trying to find a good production plan for managing the energy demands. And we worked on that, and it was really interesting because there are some counterintuitive results that we found for some specific settings. So I will go perhaps a little bit further. So the objective is...
We have 15 more minutes, and yes, and we want to have some questions. And so yeah.
Okay. So I will go just a few minutes on that, and I will tell you two words on remanufacturing. Okay, though, if we look at these single battery settings, what was new in terms of lot sizing problems is the rules that are imposed by the battery management and the energy markets. And what we have to do is to minimize the total cost, but here we have to take into account the reward received by the performed curtailments. Okay, so I will not detail, or perhaps I will come back to that if you have some questions on all the lot sizing aspects. But what I wanted to tell you is that we used some mixed integer models to solve the problem. We have to deal with some non-linear aspects because of these rules imposed on the curtailments. And we we derive some linear program by using McCormick linearization. So this is a classical way of dealing with the non-linear MIP formulations. And then we set up some graph algorithms to enumerate the possible curtailments. And we found some polynomial cases when we discretize the amount of energy, not both in each curtailment. So this is a strong assumption, but it is rather interesting to analyze. And for the multi-battery settings, we used some really classical methods in lot sizing field, which are the relaxant fixed heuristics and also the Lagrangian-based heuristics. So those are two classical methods to solve this problem. Okay, so a very last word on the third application is remanufacturing. So remanufacturing is also a very promising field in lot sizing. The context is to try to go to do the transition towards a circular economy imposed by some legislations. And how can I define the remanufacturing objective is process. It is just a way of rehabilitating some used products. So if you look at this circular economy picture here, we have many ways of dealing with circular economy, so reusing products, remanufacturing or refurbishing, and recycling. And it seems that in terms of carbon emission impact, the best way is to try to obtain new or like new products by trying to refurbishing parts of the used products. So this is the best way. I mentioned here two surveys in this field, which are really recent and interesting to deal with these circular economy problems. So we worked with some other colleagues on a 3-echelon remanufacturing system here. So we have some used products that are returned here, and we have to disassemble these products. Some parts are discarded. Then we refurbish these parts. Some parts in these processes are also discarded. So we start from the recoverable parts to the serviceable part. And then we reassemble what we can reuse to obtain what we called a remanufactured product. So this is the global picture of the remanufacturing system that we consider in this application. So there are some assumptions. We only have a single type of product. We have some identical bill of materials, uncapacitated processes, dedicated refurbishing processes, and we consider that the unmet demand is lost since we are not sure about getting the sufficient amount of returns. And some components are defective or cannot be recovered. So what I will just tell you two more things, which is interesting in this field of remanufacturing. Here, we have to deal with uncertainties since we don't know what are the amount of returns, what are the yields in disassembly processes, and what are the demands regarding to these items. So in the first two applications, I propose some models in deterministic settings. Here we have to deal with uncertainties. And we try to solve these uncertainties by, so I will, go faster, with some exact solution approaches, okay? And so this is a joint work with Franco Quesada and Céline Jiquel. We have two papers already in this field. And it was really interesting to address these problems with exact methods. the framework was multi-stage stochastic programming. So we have to at each stage, we have an observation of the uncertain parameters, and then we have to take a decision. For the following step, we observe the realization of the uncertainty, then we have to decide for the next stage, etc. So this is the best way of dealing with uncertainties. And we use the scenario trees to represent the uncertainty. And what is nice when regarding at these scenario trees is that you can come back to something which is close to a deterministic problem, but here you have to deal with a very large size, because here you are not dealing with periods, but you represent some nodes, and the size of the scenario trees can be very large. So I will perhaps stop there. I just can say that we use the two main solving techniques, one related to polyhedral approaches to provide some valid inequalities for solving these milk models, and the other one dealing with another formulation based on dynamic programming, which is called stochastic dual dynamic integer programming. Okay, so there are advantages and these advantages for both of the approaches, but we show that we can solve relatively large instances by introducing all these algorithmic ingredients to get some efficient solving methods in this case. So sorry for the time. I think I used mainly all the 1 hour and a half time, and I can answer 2 questions if you want.
Yes, no, thank you very much, Safia. And we thank you. Yes, it was really a good explanation about load sizing. And I'm very happy that you explained also some applications. So, les recuerdo a todos que pueden levantar la mano y hacerle su pregunta directo a Safia. Si no, en el chat le pueden hacer la pregunta en español y yo se la hago en inglés, o como quieran, ¿verdad? O aquí por el chat. I will start with a question that Federico Trigos asked you for the first problem. Could you please elaborate a little more on the meaning of the carbon emission constraints? Are you including the cost of government penalties? So why not to change the profit objective function? I think, yes, this is the question.
You mean that profit?
Yes, the first problem.
Okay. I will just, so this one.
Yes,
carbon emission. So the modeling of this carbon emission. So here we just looked at some constraints and nothing in terms of cost. So I don't know if the question is related to the cost.
Yes, the meaning of the mission. Why are you considering emission? I don't know, Federico, if you want to explain a little bit more your question.
Yes, thank you, Jasmine. If I didn't understand quite well how you included the carbon emission control. Is that like a cost? Is that like a penalty? Because if it's like a cost that the government will impose you for doing some carbon emission, then probably if your network is capacitated, then it would be interesting to transform from a cost objective function to a profit objective function and see what is the best way to balance the inventory versus the carbon emissions cost in this regard. Or I don't know if I understood incorrectly.
Yeah, I understand the question. So there are many ways of modeling these carbon emission aspects. You're true. I didn't mention all the possible ways of modeling this carbon emission. There are what we call the cap and trade. So perhaps you can limit the carbon emission, but also you can just buy some units if you need more emission in your model. Here, what we considered in the model is, I will come back to the constraints perhaps here. Here, what we just considered is that each time we supply one unit, we have an impact in terms of the amount of carbon emission. So it's not a cost, it's just something which is related to the amount of CO2 related to supplying one unit for one mode, for one, supplying mode. So you produce at one location, and then you transport, you use a transportation, for instance, mode, and that for one unit, it will derive an impact in terms of carbon emission. And what is represented by this capital letter is the upper bound that is allowed over a given period or over a whole horizon. So it's not a parameter related to cost, it's a parameter related to the value of CO2 emitted when supplying the product. So I don't know if I answered the question, but there are some other models dealing with that. So there are some trade, cap and trade, so you can just buy and some units of carbon that you need to produce something, but we are not in this setting.
And how do you select the value of Emax at T?
So we didn't get some real values, but we know that in European legislation, we know that for some companies, they can have a limited amount of units that they have to respect over the horizon for huge companies. So we saw in the literature that these parameters can be defined in some specific application, but I didn't work on real data, so I cannot elaborate on that because we wanted just to see if we can have a model that embed these kind of parameters, but we didn't get any real values to test them.
Yeah, a similar problem is when you are...
Sorry, Federico, sorry. We have very short time. I'm very happy that you are interested in this subject. We have one more question, I think, from Omar, and then I will have to stop Thank you, Federico, sorry.
Okay, sorry.
Yes, Omar, please.
Hello, Safia, nice to see you
again. Hello, yes, hello, nice to see you also.
Yeah, I have a question about the context of the optimization problems. In some contexts, lot sizing decisions may be strongly related with sequence decision, mainly within the planning periods. So the question is about, there are any similar approach regarding generative value inequalities, but for these integrated approaches, taking account lot sizing and scheduling decisions?
Yes, so you mean that, so we have different classes of lot sizing problem. We have, you're right, we have some what we call integrated lot sizing and scheduling problems, where we have some more detailed modeling of the scheduling constraints inside the lot sizing problem. But there are some works on valid inequalities in this field, so some of them exist. The problem is that I am not sure that since we have to deal with these scheduling constraints, these inequalities are not really, do not improve, for instance, the linear relaxation bound, really, because of this scheduling part, which is really, in terms of the structure of the linear models, it is really important. So there are some works, but I'm not sure. There are some negative results regarding these approaches, unfortunately. But still, we have some valid inequalities.
Yeah. Okay. Thank you.
Okay. You're welcome.
Thank you very much. Thank you so much, everybody, and thank you, Safia, for being here.
Thank you. Thank you. Thank you to all of you.